Take it away.
Okay. Yeah, geology and geotech. It's pretty much, geology is the first 5 weeks and it's like straight geology. It's all about rock, soils. It's kind of like a year 10 science review. It's like weathering, erosion, the rock cycle. So it's pretty non-technical in terms of there are no equations or anything you need to memorize. There's no formulas. It's all
Rote memory.
Yeah, pretty much. It's a lot of rote learning and it's all quite objective. No, subjective. That's the one. And then the last, it's half of week 5 and then the last 4 weeks are all geotech. You get a booklet, which is great because it has everything you need in it. It has all the equations, it goes through in order the topics, it has all the workshop questions all bound within that one book, so it's pretty much all you need for the second half of the course. Which is pretty much my second slide, if it wants to change. There we go. So everything is provided for you in this course, you don't need any other textbooks. You can do your own research, but that's just like a lot of Googling different types of rocks and things. You don't really need you don't need to look up literature or papers or anything. It's all written out pretty well. For geology, you need Kurt's notes. They're in a PDF form usually. It's good to read through it, but a lot of it is just rote learning, and a lot of it, apart from the quiz, you can just look it up when you're doing your assignments and things. So it's like you don't have to memorize much for this course.
So it's like open.
Hey?
It's like open.
Well, because you have the workshops and they're part of your assessment, so it's just doing the workshop questions, which you have access to the internet. I believe your quiz is closed book, so you'll have to memorize things for the quiz, but they're more sort of, you don't know what's going to come, so you just need to be able to sort of adapt what you've seen before to what you get. And it's all based off, he usually bases it off your like ZID number.
So make it easier to see by turning these slides.
And then, yeah, the student notes of what I was talking about for the second half of the course, it's all in order, it's really easy, it gives you all the equations. They go through it in the workshops. You do the first like 3, maybe 4 questions that are in that book in the workshop, and then the rest you can study. And I'm pretty sure, I don't know about you, but I just studied out of that book for the final. Like, I didn't find any other extra things. It was just that. So for geology, I suggest coloured pencils. Kurt loves coloured pencils. Pretty much, if you ask any geologist, I work in a company which we're half engineers, half geologists. They all say half their degree was just colouring in. So try using coloured pencils. I can't say it officially, but I'm pretty sure I got bonus marks just because I used coloured pencils. And it was literally like brown of the soil and blue of the water, and that's all I used. And he was like, great. So yeah, grab yourself coloured pencils. That's that. The term outline. We have week 1 is plate tectonics, geological time and minerals. Plate tectonics and geological time, it's good to read through, and it's more just like context. It's not actually tested anywhere in the course. So it's very just like good to know, it gives you sort of perspective of how things were created, when they were created. It's a lot of just talking about like how, where sort of humanoid life is like so recent, and geology and everything goes back like to the start of time, pretty much. Week 2 is the rock cycle and rock formation. It's usually when you do your lab, but I think you can pick your rock lab anytime in week 2 or 3 usually. The rock lab's really easy. You literally just go in and look at a bunch of rocks and they tell you what they are, and yeah. They ask you questions, but it's not assessed on the questions that they ask you. It's just assessed on attendance. Week 3 is structural geology. This is actually quite an important topic for your quiz. So structural geology is when they go through all the sort of defects in your rocks. It's really important to actually have a good understanding of that for your quiz, because that's half the questions they ask you in quiz pretty much. Week 4 is soils. Soils in this course is quite generic. They don't go into depth like they did in soil mechanics, because it's all covered in soil mechanics. So this soil is very much just like how do soils form, what type of soils do you expect where, and stuff like that. Week 5, you don't do very much. You kind of, the first lecture, usually the first lecture is still geology, but they say it's a review of geology. Use it just like as a Q&A for the quiz pretty much. Anything you don't get by week 5, just ask Kurt in that lecture. The second lecture is where you start Geotech, but they don't go very in depth because they know that week 6 is off, so they don't really teach much in that first Geotech lecture. And then week 7, you have bearing capacity of shallow foundations. I was also looking at the assessment guideline that stitched you up a little bit because your assignment's due on the Monday and then your quiz is on the Tuesday. So yeah, I was looking at that in the online course outline. So pretty much my suggestion would be try finish your assignment by at least the Monday or Tuesday of that mid-sem break week, and then Wednesday, Thursday, Friday, try be doing 1 or 2 practice quizzes before the quiz, particularly because you don't have your notes. And then you have settlement of shallow foundations, design of pile foundations and lateral earth pressure, and design of retaining walls. All of them are assessed in the final, and no geology is assessed in the final. So pretty much 50% of your marks are geology, 50% of your marks are geotech. Geology is your homework, your rock lab, your quiz, and your assignments. And then your final is all geotech and all workshop question-based type questions. Yeah. One thing to point out about retaining walls is they're actually quite content dense, the retaining walls, and it's the last subject, so the last topic. So I feel like a lot of people sort of focused more of their study energy on the other parts of geotech because they felt more comfortable with them. But for us, there were 3 questions, and the last question was retaining walls, and it was worth like 30 marks or something. So make sure you still study retaining walls, even though it's the last topic. Okay, yes?
What did you say the quizzes and so forth? So assignment is on geology?
Yeah, assignment, but there's part A and part B of the same assignment. I don't know why they call it part A and part B, because they feel like 2 completely different assignments.
Yep.
But they're a hand-in task. You get weeks. One of them is both of them are group tasks.
Oh.
So make sure you pick a group that will actually do the work with you. It also involves a field trip that you have to do external to the class. So you have to like make a time with your group and go to, I don't know if it's in Bronte this year, but usually it's Bronte.
I don't know.
Oh, really?
Looked at videos of Kurt going to these trips instead of us.
Kurt usually goes out once to Bronte, so you can ask him when he's going or if he's going. And if he's there, you can ask him questions the whole time, and he'll pretty much, if you ask enough questions, kind of give you the answers of what you want.
It's like a school excursion.
Yeah. Well, it used to be a field trip. It used to be actually in one of the classes, but then I think COVID messed that up, and then they couldn't fit it back into the timetable for us. So they just said, you have to go with your group whenever you can. But it's really chill. It's really easy. Okay. Are there any other questions before I start content? I'll come back to more about the assessments later. No? Fact. Week 1, geological time, plate tectonics. It's good to read over, but as I said, it's not really assessed again. In terms of geological time, it's broken down into lots of different periods, but they're quite arbitrary depending on where you get your information from, where you are in the world. Like different continents divide it differently. and then they go into further divisions again. So it's very sort of like you have, for example, Mesozoic, yeah, and then that goes into like the Jurassic period, the Triassic period, and then one other one that I always forget.
Yeah, that's
But-
talking about.
You read it once and then you never use it again in the course, so it's not too important. Plate tectonics, I'm pretty sure we all did this in like science in year 10. You have divergent boundaries, which are the ones that are moving apart from one another. If you have two oceanic plates that are moving apart from one another, what happens is magma comes in and forms more oceanic plate. So it's pretty much like the plates move apart, magma comes up, and there's more plate there. So yeah, it's just building plates. If it happens on land, you end up with rifts and rift valleys. It's pretty much just a huge crack in the Earth's surface. Nothing really fills it in. You just get a very steep on both sides kind of rift down the middle.
It's like a ravine in Minecraft.
Then you have convergent boundaries, which are when two boundaries are moving towards each other. Different things happen depending on what boundaries are moving towards each other again. So if you have two continental boundaries moving towards each other, they usually both go up and form a sort of mountain range. So because they're both the same kind of density, as soon as they hit each other, they decide to push up together, which is why you get a lot of mountain ranges where two continental plates meet. For example, the Himalayas. Then you have oceanic and oceanic plates. What happens here is they pretty much just crush each other. So when two oceanic plates go together, because they have all the water pressure on top, they can't really push up against the water pressure. So they just, one of them like breaks and then pieces just kind of go everywhere and they just keep pushing. So no sort of, what would you call it? It's not an item, no sort of like geologically significant thing happens there. They just break. And then when you get a convergence between a continental plate and an oceanic plates are heavier, so oceanic plates will subduct under the continental plate. What happens is just offshore you'll get a big deep ocean trench. So it's you can imagine two plates going together, one goes down, so you get this almost V shape where one's gone under the other. And then what happens on the other side, on the land side, is on the land side, this oceanic plate starts to melt, and a lot of the time you get volcanoes right near the edge of the continent because all the magma is only just under the continental plate, so it kind of pushes up through. And also you think if this has just gone through a big like pressure resistance, it's going to be a little bit more brittle and a little bit more porous, so magma tends to come up and create volcanoes and things like that. Yes?
What was the name of the plate that's not the oceanic plate?
Continental plate. And then the last type of boundary is either called a conservative boundary or a transform boundary. It's when the boundaries slide against each other. So one's moving forwards, one's moving backwards. They're not necessarily moving towards each other, away from each other. They're just like sliding next to each other. This is where earthquakes happen. So if you've heard of the Ring of Fire, it's pretty much a oceanic plate that sits just around the Pacific Ocean, and it always gets caught. So pretty much for transform boundaries, earthquakes occur when like two transform plates are like sitting next to each other trying to move past, but they're being held on by a piece of rock or like some type of friction between the two plates, and then earthquakes happen when that friction eventually is overcome by the shearing force, so it just creates a slip, and then the vibrations that go out are a earthquake. Again, plate tectonics, it's kind of like year 10 plate tectonics. You also don't really come back to it. So it's good to read through, and there's a lot of information on it in Kurt's PDF, but you don't get assessed on it in any of the assessments. It's, again, more for context. And then the last part of week 1 content is pretty much just giving you an understanding that rocks formed at lots of different points in time, and at those points in time there were lots of differences. For example, different climate, different atmosphere, different water levels, and like different pressures. So that has a big impact on the type of rocks and also the features in rocks that you find. Yeah. Fab. So that's week 1. Are there any questions about week 1? Cool. Week 2, sorry, I got really lazy with all my photos. I'm not very artistic at all. I'm an engineer in the end. Week 2, what was week 2? It was minerals, and then it was just like rock classification and things. It's when you do your rock lab. Pretty much stratigraphy, I don't know how to say all these words, I always just type them and never say them out loud. It's pretty much just a logic that says the older rock is going to be below the younger rock, because as rock is forming, you have the formation of bedrock, you have more sediment or whatever. Well, I guess this is really in terms of sedimentary rock. You have more sediment that comes on top. It forms the next layer of rock, you have more sediment. So the top layer of rock is the youngest. And then as you go down, it's the oldest. The only sort of exception to this is domes and basins, which are 2 different defect types, which I'll go through later. But in general, younger is on top and then older is underneath. They are made up of lots of different minerals. Minerals are inorganic. Usually to define them properly, you need like chemical analysis and X-ray, because you're looking at the different types of structures, crystals, how they formed together type things. But in reality, no one has the time, money or effort to do that for every single rock that they come across. So you then revert to just physical properties. There's 11 physical properties that get talked about. They all have definitions in the notes. I'm not going to go through all of them, but they're very just normal. Transparency is like, can you see through it or not? Hardness, there's something called the Mohs scale, which is pretty much 1 to 10 of how hard a rock is, and it has a rock per level to set out a scale of, is it harder or not as hard as this rock, pretty much. 1 being something like chalk, which you can easily scratch through, and 10 being diamond, which it will scratch something else. Colour, obvious. Streak is, does it have anything that is a bit, not strange, but like different colour running through it, something like that. Crystal form is like how big are the crystals. Yeah. That's pretty much just a bit of rote learning. You don't really need to memorise it because the quiz doesn't have anything. I mean, it would be good additional information, but describing these factors in the quiz would really be going like above and beyond. It's not expected, and it's not what full marks in a previous quiz put in. Like, so then is it like, do you need it or not? I work in this company called PSM. It's a geotech company. We do a lot of field work, tunneling and mining. And pretty much from all the field work I've done, a lot of geology is about how it looks and feels in the field. So like feel is really important because you can often feel like grain size or things like that. So it's a lot about just kind of like physical. Again, it's all physical properties. You don't send the rocks that you find in the field back to the lab every time. You just do it by touch on the spot. Any questions about week 2? No. Okay. Rock Lab as well is focusing on different types of rocks. So there are 3 different types of rocks: igneous, sedimentary, and metamorphic. Igneous rocks are made from the magma, so the mantle layer of the Earth's crust. They change depending on whether they're intrusive or extrusive. Intrusive being they form underground, and in confined pressure, heat, they stay underground. A big key factor of intrusive rocks are larger crystals. So the crystals have more time to form because the rocks that are formed underground cool at a much slower rate. So as the rock is forming, it's cooling down because it's turning from its liquid state into its solid state. Because it's still underground, it's still close to other magma, so it does it very slowly, and so that's why bigger crystals form, for example, in granite. The other side of igneous rocks are extrusive rocks, and so they're the ones that form pretty much from either like a volcano eruption or a lava flow or any of that. They cool very fast, so they don't have time to pretty much form crystals. They have the same minerals as the intrusive ones, so technically crystals can still form, but because of how quickly they cool, they don't have the time to. An example is pumice. So if you have ever seen pumice, you'll know that it actually floats. It's because it cooled so quickly, because that's during an eruption that all the gas bubbles that were inside the magma cooled inside the magma. So it creates holes and it's a very permeable rock. Whereas another type of extrusive rock is basalt, which is from a lava flow. The basalt? I'm pretty sure it is. It's from a lava flow that cools on like the side of a volcano. Pretty sure it's basalt.
Basalt is the most common volcanic rock type on Earth.
Is it an extrusive?
Extrusive, yeah. That's the one
That sounds right.
That's the one I'm thinking of. The next type of rocks, sedimentary rocks. Pretty much think of sedimentary rocks as dirt that's been glued together by soluble compounds. So sedimentary just means it's made up of lots of different sediments. So it can be gravel, sand, clay, silt, whatever. Sandstone. Most of Sydney is Hawkesbury sandstone, you'll find out. They make you do things with like geological maps, and you see that pretty much all of Sydney's CBD is on sandstone. It can get quite interesting because it actually affects the way we tunnel. If you look overseas, a lot of their tunnels are really quite circular, whereas in Sydney, all of our tunnels are quite flat with only a very small arch over the top. Yeah. So if you go overseas, for example, like Switzerland or Germany or somewhere, you'll see this shape of tunnel, but in Sydney, you'll have this. The reason being, sandstone particularly has very high horizontal stress. So if you were doing this, you're removing more like horizontal stresses that could hold the rock back. Whereas if you only do it to a certain point, this whole bar of sandstone on top will sort of push against each other and keep itself in place rather than falling. That being said, you still have to rock fold the top because it still has potential to fall. And then the last type of rock is metamorphic rock. This is any type of rock that has undergone a transformation. Usually the transformation is due to pressure or heat. It can be igneous, sedimentary, or other types of metamorphic rock. So I used to get confused because I used to think it was only sedimentary rock that had undergone heat and pressure and then it turned into metamorphic rock, but it's not. It's any type of rock that undergoes a transformation. Classic example is marble. So pretty much as limestone gets heated up, it doesn't reach a melting point, but it reaches a point high enough that its structure changes. It doesn't melt, but it almost melts. Does that make sense? Yeah. It's a marble.
It's well.
Yeah.
Heat pressure or just heat?
Both. Heat pressure. Usually, it depends on what type of rock is metamorphosized. Crystals can grow bigger, but because you're working with whatever sediments or whatever the old rock was made up from, it sort of narrows down what it can be turned into. If that makes sense. Another thing is, if you have, say this is all like a limestone wall, and you have something like a dike coming up, which is just magma that's shut up through a defect in the rock or something, and this is limestone, you'll have a section that turns into marble, and then you'll have another section next to it that hasn't quite turned into marble yet, but it has had some effect of the heat on it, and then you have limestone out here. So there are sort of like transition zones sometimes, that's sort of like a grey area of, it's not completely metamorphosized rock, but it's changed from the original structure that it was in. But they don't go into much detail of that. I just thought it was good to point out that it's not like heat gets to this point and then all of this has changed. There are differences.
Is that still considered metamorphic rock?
That's the question. So like, in my quiz, if I actually did get a dike. I think almost everyone got a dike in the middle. I noted that it was a grey area. I noted that it would have some properties. For example, bedding planes are only in sedimentary, but you would have some bedding planes that you could still see in this area, and then you wouldn't really have bedding planes in the marble. So it's very kind of has features of both things. Yeah. Cool. And then that's pretty much the rock lab. They just hand you different types of rocks. You look at them, you say that's cool. They'll hand you a microscope to try to look at some of the crystals closer. It's actually quite interesting, but it's you don't get that much out of it.
Do you have any calculations?
In geology?
Yeah.
No. No, that's what I mean. It's so subjective because there's no calculations.
Yeah.
There is one sort of chart thing that you have to learn how to read, but that's literally it's 80% of this and 20% of this, so I'm going to draw my line so that 80% of this, the line is on this side, 20% is on this side. It's not calculation at all. Yeah.
So what are the exam questions like? Are they just word?
It's drawing rocks.
It's drawing
Yeah. So I'll give you an example of the quiz later. I actually had a photo of part of mine earlier. Oh yeah, there. So this was part of my quiz. So
looks like a
they
kindergarten drawing. No offense.
Why?
It's good. It's just part of the course,
Yeah, so it's literally just drawing and then labeling things. I'll go through the quiz later, but it's it's not hard. Yeah, it's that is geology to a T. All the geologists at my company pretty much say if the engineers knew how easy geology was, we wouldn't have a job. They're they could do our job for us in 2 seconds, but we just like to keep them around because they're more fun. They tend to go out more than the engineers. Okay, was there any questions on week 2 before I move on? No? Fab. Week 3 is structural geology. This week is really important to learn for the quiz. So a lot of this stuff is what you can be asked in the quiz. So I'll go through the quiz later. I keep going to talk about the quiz, but anyway. The main defects in rocks are bedding planes, which are only sedimentary, unconformities, joints, folds, basins and domes, and faults. So, bedding planes is pretty much one layer of sedimentary rock occurs, and then there can be a however long time period, and then more sediment is deposited on top and then forms its own layer of rock. There is an interface between them, but usually it's a little bit weaker than the rock mass itself because it's not two different types of rock, but the layers of rock can form in different environments depending on how long it was between the sediment being deposited. And so you pretty much, oftentimes you get quite planar bedding. So you'll see when you go to Bronte, which is one of your assignments, you'll see in the cliff face there's just like practically parallel lines. They can kind of look like this. It's not straight lines the whole way down. They can change up a little bit, but pretty much you'll see that they're parallel to the ground. Angled lines can form. That's usually when sediment's being traveling down a slope or something, and so then it just creates an angle as it's being deposited, and then it just creates bedding planes in that angle. So for example, like the bottom of a river or something, if it's flowing downstream, sediments is being deposited in that sort of downstream angle, and then your bedding planes will be in that angle.
Is there some like visualization I can do for that?
So pretty much if you have like your river's coming down this way and then it's flowing this way, you get like sediments also deposit depending on how they're being deposited by density. So you'll get bigger sediments up here, more like the gravels, and then as you go down, you'll get gravel, sand, which are smaller, silt, which is I can't draw any smaller again, and then you'll get your clay particles last because they're the smallest type of particle. But yeah, as this is being deposited, because this is on an angle, the bedding planes will then run in line with that. And so if you take a cross section this way, it'll look like they're angled, but it's actually just the direction that they were being deposited in when it was formed.
Is that alluvial?
That is alluvial / marine. Marine is usually, difference between alluvial and marine, this is soils though, not rock, but that's okay. The difference between alluvial and marine is alluvial is usually around rivers, so flowing water, whereas marine is the bottom of seas, so it's less stirred up, it moves less, it stays quite where it is. And so if all of this makes it down, you'll have a basin of marine sand which will be in density form. So that's when you get the graded bedding, because these will drop because they're higher density, and then you go up in particle size density pretty much. Any questions on bedding?
Like draw the bedding and like
In the quiz?
yeah.
Yeah.
Like
So-
this was limestone.
Limestone, yeah.
Draw
That would be good enough for like sandstone, limestone, siltstone, shale, mudstone. Like, as long as you have said that you expect bedding because it's a sedimentary rock, whether you get it in the right angle doesn't matter too much. More just that you've identified that it would be there because it's sedimentary. And there's like different layers.
Oh! Wait, you kind of made it on time, like the.
Ah, great.
Yeah. Come learn about rocks and sand. That's where the
Okay.
magic happens.
Yeah.
Is that sand?
Sand.
That's what soil is.
Yeah, so that's bedding planes. Joints, I decided to talk about joints next because people often get confused between joints and bedding planes when you're identifying them in the field. Because they look quite similar, they often just look like cracks, but they form differently, and you need to be able to, particularly for the field trip, identify the difference between. I remember I went up and asked Kurt multiple times, being like, is this a bedding plane? He was like, no. And then I was like, is this a joint? He was like, no. Because what happens is you have bedding planes, and because there's sort of weakness between the bedding planes sometimes, because it has been years or millions of years between deposition of sediments, you can get weak planes, and then those weak planes can kind of form like cracks, where the weak plane or the like more shit sediment pretty much has all been eroded out, and so it looks like a joint has opened up this way, but it's still just a bedding plane that no longer has a fill material, if that makes sense. So it's still a bedding plane because it has formed as a bedding plane, it's just a bedding plane that's been eroded. Joints, on the other hand, are pretty much cracks that are formed by tension and compression forces. So if you have...
Should we take a photo of the wall?
Sure.
Yeah. Okay. Which side do you want wrong time? This one?
So if you think about a piece of rock, like this, and you have compression forces for whatever reason on these two sides, usually it's just confining pressures, because there'll be like rock and other things still on this side. It's pushing, it has high horizontal stress. Sometimes what can happen is it ends up sort of, it's almost like a buckle, like this, with the pressure still forming this way. And then what happens up here is you get like a steel beam, you get tension on the top, and then you get these joints forming, which are pretty much cracks because the rock is being pulled apart. And so that's a joint. Another way I can describe it is, which this is almost an old quiz question. So you have like a big thing of just say sandstone, bedding is forming this way, whatnot. For some reason, over time, you have water flowing down this way. It's going to create a very big valley. This valley itself is not a defect, that's just like a geological structure. But because you have high horizontal stress this way in sandstone, and this confining pressure has been moved out, there's nothing confining it anymore, you find on the sides of valleys you often have big vertical joints that run down. So these open up because there's nothing holding it back from wanting to move in towards the valley.
But are joints basically just like vertical?
Joints? No, they can also be horizontal.
Oh,
But
if it's between bedding planes, it's not a joint.
not usually. No, it's highly unlikely that if, particularly how you can tell is if it's still in line with the rest of the bedding planes around it, it's more likely a bedding plane that's just been eroded away. For example, if there was something that was very definite and looked like a crack this way against bedding planes, that's more likely a joint. If that makes sense.
Can I be a right?
Hey,
Can I
sure.
be a right? Yes. What would this compression force be from? Like in real life?
Like other. Wait, what do you mean?
So like this is your groundwater. What would cause this compression?
Like other soil, like the surrounding.
Just imagine like, remember back in the first topic that Millie was talking about?
Yeah.
Tectonic plate movement, right?
Oh yeah.
That drives all these like processes, right?
Yeah.
So it's squashing it together. And it's because tectonic plate movement's horizontal, that's why these cracks will only form like vertically, because yeah.
Oh.
You can probably explain it better. but-
Mostly vertical. But
Mostly vertical.
horizontal.
Yeah. But yeah. I don't want to say only vertical because that's not true. They can form horizontally as well. Usually horizontally is like if this is under a huge load. This doesn't usually happen in rocks too often, it's more soils, but if this is under a huge, say it has whatever, 1,000-story building on top of it, and then suddenly you take that confining pressure away, which this rock has reached an equilibrium with, it can then have almost like a decompression force, and then you can get joints that happen that way. But highly unlikely, most of them are vertical or almost vertical. Yeah. Yes.
So could you re-explain like what's the context of the top diagram? Is that
This top diagram?
Yeah.
So pretty much, this was a past quiz question that I saw. It was like, it gave you a V-shaped valley, it gave you sandstone as your rock type, and then it was pretty much like, draw a likely layout of what that would look like pretty much. And so you then have to go in and explain that you have your bedding planes. You can say, usually people just put them parallel to the ground. You explain why this was a V-shaped valley, which I'll get to later. And it's pretty much because it was carved out by by water rather than glacier. And then up here, I was explaining that because there's no confining pressure anymore for the rock coming from this side, this rock is still trying to push against that way because it has high horizontal stress. And as soon as you release the pressure from the other side, the joint structure defect would occur because there's no more confining pressure on the other side. Yeah, I flagged that it's a common mistake and common error on the Bronte field trip that groups were categorising the weak bedding planes as joints when they're still bedding planes, it's not joints. The next type of defect is a fold. So a fold is pretty much when something like this occurs, but the rock is more ductile. So instead of creating joints, it creates this sort of wavy structure, and then it can get like closer and closer the more pressure it has on the sides. But because it's ductile, it doesn't create joints like this, it actually moves and molds to this type of shape. And you can see sometimes you'll have bedding planes that follow the fold structure. So it's often in sedimentary rock, and then you'll see that's when you can get bedding planes that are no longer parallel to the ground. They're weird shapes like this. Still bedding planes, but they've just been affected by other plate tectonic movement. Between these bedding planes, it's quite common to get shearing because they're moving. Obviously, one has to move more than the other when they start folding, so you get shearing between the bedding planes. This would be a classic example of when a weaker bedding plane during the shearing process has just been mechanically weathered by that movement. So then maybe say this part of this plane is no longer there. That's not a joint, that's still a bedding plane. Any other questions? Yes?
Wait, so the horizontal joint would only be possible if the forces were like really large externally, right?
This one?
So on the top. No,
The compression building example, like that's split apart.
yeah, that one.
I'm just talking about just seeing how this joint split apart once the decompression force is really high from the building when it floated.
Yeah.
Only because of large forces, right?
Yeah, usually. But that's highly unlikely to happen because the rock, if there's a building on top of it or something like that, you're unlikely to take the building away, or you've actually dissipated your building pressure through piles at different areas of the building. So you've actually dissipated the pressure rather than having it straight down, which is kind of soil mechanics. Yeah. Any other questions? The next one is unconformities. This is pretty much when you get really random and jarring bits of geology next to each other, and it looks really weird. So for example, if I had like a bit of rock that's like this is just like a pillar that I've taken out, you can have like bedding planes this way, and then suddenly you get bedding planes this way, or you get some type of like curvy, weird other material down here, and it looks very kind of just juxtaposing next to each other. What happens here is this is usually an erosional boundary. So pretty much this material used to be the main material. It's undergone weathering and erosion, and it's just created some type of usually quite rounded shapes, because when weathering occurs, it's quite like it rounds everything off. You have no more sharp corners and stuff. Yeah.
Oh, what is this for?
This is for unconformities.
Oh.
Yeah. So it's pretty much just when things don't look right next to each other. You can pretty much just not assume, but often the case is this was the original structure. It's been weathered down because of some type of weather event, weathering, mechanical and chemical, and then you get different deposition on top. Yeah, and then it reforms the rock.
Can I add on to what you're saying?
Yeah.
I think Millie's going into a lot of detail here because this is the meat of assignment
Quiz.
quiz, but
Quiz.
also the assignment where you go out and you look for
Bronte field trip.
Yeah.
Bronte field trip. Or you
What's
talking about
assignment
poster?
B? No, the one after the poster.
The field trip. There's the field trip, poster, quiz, and homework.
I think it's a field trip.
Yeah.
Where you like identify defects and write about it.
Yeah.
So you have to go out and do this in the field, basically.
Yeah. That's why I keep saying bedding planes and joints different. You're highly unlikely to find any unconformities in the exposed rock that you look at for the field trip, though. That's just a need to know. All of these as well have good detail written out in Kurt's notes in the PDFs. It's a lot of, again, rote learning, but these ones you actually do need to memorize because you need to put it in your quiz as well. You need to think about what geology you've been given in your quiz and then put that in for marks. He is very much a reward type system, not take away. So he rewards you for what you put in. He doesn't start at 100 and take away for mistakes you make. I was about to say if that makes sense, but I realise I keep saying that. Okay, the next one is basins and domes. They go hand in hand, they're just opposites. So a basin is when there has been a subsidence underneath a rock, and it pretty much creates like a pool sort of shape. It's very often the case with things like longwall mining. Longwall mining happens when miners, instead of creating an open pit, they go down below the surface of the earth. They mine one singular seam of coal, and then they just let everything on top settle down instead of trying to move the rest of the geology. So it's pretty much just any movement that allows rock or soil to kind of just sink. Basins that was basins. Domes, on the other hand, is an uplift of the rock, so it creates a dome kind of shape. Usually it's magma trying to come up, and it's almost like the start of a volcano sometimes, like it's some type of pressure below the Earth's surface pushing rocks up. Yeah. Key things to think about is for basins, you'll find the younger rock in the middle of the basin and the older rock as you move out from the basin. Yeah. Do we need this anymore?
I'll take a photo of it.
That's what I'm going. Limestone heat pump. Pretty much when a basin forms, it forms like this. There's been some subsidence because of some type of plate tectonic movement usually. Most of these form with plate tectonic movement. You have the younger rock down here because that was the stuff that was originally on top, and you find that because the rock moves as a whole, older rock, you can start finding up towards here. So if you took a cross section across this way, you would have youngest rock in the middle, and the further away you move from the middle of the basin, you'll be able to see older rock coming up. So that's almost one, domes and basins are almost the two exceptions to the idea of stratigraphy, which is older rocks at the bottom, younger rocks at the top. For domes, it's the other way around. So the dome, you go up this way, pretty much the younger rock is on top and the older rock is on the bottom. But if you take a cross section through here, you'll be at older rock first, and as you move away from the middle of the dome, you'll get to younger rock. Does that make sense? So if you imagine, I feel like that wasn't explained well enough. This was 100 years, this was 200, and this was 5 million. Right? If you come and take a cross section this way, wherever it goes, you'll see that this stuff in the middle is this part of this 5 million. This section here is part of the 200-year-old rock, and then this section further out again is part of the 100-year-old rock. Does that make sense? Yeah. Like a rainbow and then like a depressed rainbow. Yep. And then faults. Faults occur along transform or conservative boundaries. It's pretty much just the action of what they do. I don't know how else to explain. Shearing is pretty much two pieces of rock are moving apart along one another. You can imagine it's similar to a conservative boundary when earthquakes happen, so it's just one rock slips forward, one rock slips backwards. You have a normal slip, which is when rocks are pulling apart and they have a defect in them. Faults usually fall along, they're their own defect, but oftentimes you find that where the rock breaks already was a plane of weakness. So like it could break along a joint. But faults also are at a bigger scale, usually. Normal slip is when the rocks are moving apart from each other, and as they move apart, instead of creating a gap between them, they're still trying to be supported against one another, so it kind of just slips down. Reverse slips are the opposite, so when they're pushing against each other, there's a defect through it, so one slips up, one slips down. Between all of them, you get quite a bit of mechanical weathering, because as it moves, it rubs off sediments that are between the two rocks. But yeah. And it doesn't make the rock permeable, but it creates more opportunities for things like groundwater to get in and erode it. No, weather it more. The other part of week 3 is pretty much how to do a site investigation. It has a step-by-step guide of what you're looking for, how to classify it, for all the different rock types, all the different defect types. It's really good, and I would suggest printing that out and taking it to Bronte with you when you go to do mapping, because it's a step-by-step guide. It's pretty much exactly what they're looking for. Yeah. We actually ended up going to Bronte multiple times, so you don't have to, but it was, for the 1 hour we spent, it was, the first time it wasn't enough to get everything down for that assignment.
The group assignment?
Yeah, the group assignment. but it depends on your group, it depends how long you go for the first time, it depends how prepared you are when you go to look at the rock, because if you know exactly what you're looking at the first time, it's really easy and you do it in 5 minutes. If you were like us, we sort of thought we would figure it out when we got there, and then you're looking at it and it's like, looks like a rock. So
It does.
yeah. So yeah, I'd suggest definitely reading through that document at least before you go. Best thing you can do is take it with you. Any other questions?
There's other.
Yeah.
And you also learn more as you go throughout the weeks. So if you do a week 3 site visit, you might have learned more later on. Or is it more about just these content week 3?
Well, you become more comfortable with identifying defects as you kind of study them. You get told about the assignment in this week, I'm pretty sure. And so going there with very fresh information feels quite hard to actually use that information and put it in practice. Whereas if you want to go back, it's easier because you sort of then, you've A, seen it once before, and then B, you've had more time to sit with the concept so you kind of understand easier the second time. It's like rereading something. You always understand easier the next time. You don't take much in on the first time. Week 4, my slides just start going further and further downhill. Week 4 is all about soils. Soils are great. I love soils. So pretty much, you classify a soil dependent on its primary grain size. You learn quite a bit about this in soil mechanics if you've done soil mechanics already. You have gravel, sand, silt, clay being the smallest and gravel being the biggest. Gravel usually isn't classified as a grain size just because it's greater than 10 or whatever, but yeah. You have mechanical weathering and chemical weathering. Mechanical is the physical processes of weathering. So it's your wind, it's your water that is running past the rock, it's earthquakes, it's trees that are growing, and the roots are breaking up the rock. It's if you have, for example, this bedding plane, what can occur is something like clay particles come in and populate that defect. And then clay particles, as you add water, expand. So then that pushes out the rock and weathers the rock. Same as water freezing. So if there's water in a defect and then it freezes, it expands, so it starts to break down the rock mechanically. So mechanically is just physical processes that act on rocks to break it down. Good.
Wait, so what was that? Like when the water comes in or the clay comes in?
Yeah, so clay particles, as clay particles saturate, you would have seen it in soil. Have you done soil mechanics?
Yeah. Like,
Yeah.
is that a type of weathering?
Yes, mechanical weathering.
Okay.
It's part of mechanical weathering. Mechanical weathering is any physical process that breaks down rock. Chemical weathering, on the other hand, usually occurs after mechanical weathering because it's often, chemical weathering is after the rock has become more permeable because it's already started to break down. Water gets in and then any soluble materials within the rock dissolve, and then that's the chemical weathering. So pretty much chemical is, it's more process based, I guess. It has a physical effect afterwards, but it's due to chemical reactions and chemical changes in the rock. It's not due to physical properties. So,
Yeah, that makes sense.
that makes sense? Cool.
Of the rain.
Hey?
Like rain?
Rain would be mechanical.
Oh, really?
Yes, because it's a physical thing that happens to the rock. So if you think about rain hitting a rock mass, it's a physical impact that can potentially break off or break apart rocks. Whereas usually it's the rise of groundwater. Acid rain though would be chemical. So acid rain is a very good example of, it's almost mechanical and chemical at the same time because it's a physical process of you're hitting the rock with water, but then is it sulfuric acid? whatever acid,
Yeah.
I think it's sulfuric, or anyway, whatever type of acid comes down, that chemical dissolves anything that's dissolvable by that in the rock, and then that's chemical. So they work hand in hand. Usually it's mechanical then chemical, but they can happen at the same time. But that's sort of like an odd case. Yes.
So could you repeat the part about like when the rock is already a little bit?
Permeable.
Yes.
So when mechanical weathering has been completed, for example, you have this rock mass, you have a nice big tree that's growing out this way, and all of its roots have come down and started creating cracks and discontinuities and breaks in the rock. That rock then becomes more permeable because groundwater level, as it rises, for example, if my groundwater level comes from here and rises up to here, it's easier to get into these cracks now because it's not a solid rock mass anymore. So as rock becomes more permeable, it is more susceptible to chemical weathering.
Would you say that like chemical weathering is anything that you could potentially draw a chemical equation or
Yeah.
chemical reaction?
Yeah, it's all chemical reactions, which is,
So groundwater's got something that would react with
yes.
rock. Yeah, and
Yeah, groundwater, I don't want to start getting quoted on groundwater, I don't know enough about it. I'm pretty sure it's not potable, obviously, because it has other dissolved substances in it that if we ingested as humans, it would not be good. If that makes sense. Okay, after weathering comes erosion. So they're two completely different processes. Erosion is the movement of soil. So after it has been weathered, usually it's sort of particle size, or it can be boulders and things like that. Erosion means it's getting taken away and moved. So usually it's either wind, it's rain, it's water that flows over the top that picks up the small sediments and moves it downstream. It's anything that moves the soil afterwards. Another side note is residual soil is soil that you find in the place that it's been created. So residual soil is, for example, this rock has been broken down from sandstone and there's now sand sitting on top of the ground. This is residual soil. It can move within, I don't want to give a specific distance, but it can move from that site. But if it's in the general environment in which it's created, it's residual. The other option is fill. Fill is when usually geotech engineers come in, they're like, this is good soil. I want this soil over here because I want to build a building on it. So fill is just when it's soil that's in a completely different landscape to which it was formed. Usually it gets taken because of its properties, or it's bad soil / contaminated or something, so it's been moved to create a foundation for a building that it's going to be buried anyway, so it doesn't matter. Does that make sense? So residual is where it is, fill is where it's moved to.
Construction 2101.
Yeah. Cut and fill. That's in one of the courses.
Yeah.
2101?
And I think it's in soils too, maybe. They might have talked about it. But it's definitely in 2101. It's like, do you remember when they're like cross sections of like the road oil and they do the cut and fill? It's,
Oh, that's the one I want.
This always gets me in the beginning.
yeah.
My whole thesis is on fill. So we had, I probably shouldn't talk about it too much.
Top secret.
Pretty much there was a site that's gone kind of wrong, and I'm now testing the fill soil to see why
It's sponsored by PSM.
I wish
thesis,
it
right?
was.
Was it? It's full work there, right?
It's full work, but it's part of my undergrad, so I don't get
So
paid.
they don't get it. Oh,
But I was thinking, like,
But if I write a paper on it after, I will get paid.
I was thinking like Rosa Lincoln, because you said that was what, like,
That one's asbestos.
Asbestos.
oh.
So asbestos and PFAS are the two main contaminants of soil. I was on a site last week that had both PFAS and asbestos contamination. It's not fun.
That's
It
great.
was one of those like 36-degree days. You're in full PPE anyway, and then you have to have a hazmat suit on top and a mask, and you're just wet. It's not fun. Anyway,
Oh, can I bring up something?
Yeah.
You call it PFAS, right?
Yeah.
I call it PAS. It's like acid sulfate soil, right?
I don't know. It was that
PFAS.
PFAS was that like No, it's like a fire retardant chemical that they had in like the 70s or 60s or something.
Oh, okay. I'm
That-
talking about something else. Right.
They thought it was great at the time because it was really good at killing fires, but then they realized that it never breaks down
And it's bad for you.
and it's bad for you.
Yeah.
There's a whole, I think it's called Williamstown or something, that's all contaminated. Anyway, I'm almost done. I realize I've been going for a very long time.
Right.
This is the last week of content for geology. You have different types of soils. The different types of soils are just dependent on where they've been created, and you have expected sediments and things based on where you are. Alluvial is like rivers, so it's a lot of sand and silt. As soil travels, I said before, by density, it generally drops out. So for example, this was another thing. Can I rub it out?
Oh, I'll take a photo of that. Maybe you can rub out the bottom right there. I think that's all.
Yeah.
Yeah. Yeah, you can do it anyway now.
This was another thing that got asked, well, that was in a quiz, previous quiz. You had a river, and then you had big floodplains on either side, so pretty much quite a flat area. And something that a lot of people needed to know in order to get marks for the quiz was that in a flood event, as water travels up and out of the river, you get the same type of graded settlement as you do in a normal river downwards. So all the bigger gravel sand particles were here, and as you moved out, you got smaller silt, and then clay particles traveled furthest. So it's just that kind of logic as like, where would things settle and why would they settle there? Yes?
Okay, so how does this section, like the types of soil, differ from like the top part? Like what are you talking about with the 5 different types there? Like what specifically?
It'll be what the main component of the soil is. So alluvial, pretty much sand, marine is pretty much sand, but aquatic sand, so like water-based sand, not water-based sand, but like sand, water around it. Aeolian is like desert sand, so it's still sand, but it's just in a completely different environment. Glacial has obviously water, ice, all of that. It happens to have a lot of boulders and things because when avalanches or just any sort of ice movement occurs, it has a lot more force, so it has the ability, if you have ice / a glacier sitting on top of a valley, something like this, and then it comes down into the valley from some type of avalanche or some type of movement, it's more likely to bring big actual like boulders down, whereas a river isn't going to have the, I guess it's all like kinetic energy to move a boulder. So yeah, glacial has boulders all the way through to like silt. Colluvial is just dirt. I don't know how to explain colluvial. It's kind of like slightly further out than alluvium. So it's just almost the general. I don't know how to explain colluvium.
That makes sense.
Yeah, it's more. Usually, you'll probably get clay particles in colluvial. Yeah. And then the last thing I'm going to talk about are the different types of valleys, which often these types of valleys occur in the quiz. You have your V-shaped valleys, which is what I was talking about before. The V-shaped are dug out by water. So if you have a stream or like a waterfall coming off the top of a mountain or cliff edge, the longer that waterfall is coming, it has the potential to bring pieces of weathered rock with it. So imagine you have, I'm gonna rub this one out. If you have a cliff face and you have a waterfall coming down this way, it has the potential to start taking off pieces this way until it works its way back, and then you end up with almost like a stream down this way. This valley, because obviously either side into and out of the whiteboard you still have the rock where the water wasn't flowing. This valley is going to be a very sharp kind of V shape. So that's when it's carved by water. I probably misled you here because this, if it's a glacier, will be U-shaped because it brings down boulders and the boulders take anything in its path with it. So if you imagine like a 2 meter wide boulder coming down from a glacier melting or something, it's going to carve out a very U-shaped valley. You'll also in glaciers have what are they called, striations on the rock, which are pretty much just like scratch marks on the rock, and it can often be quite slickened, so it can be quite smooth after a glacier has gone down. Yeah. Any questions? Fab. The last thing I'm going to talk about, sorry for talking so long, are the assessments. So, your first one is homework and the rock lab. It's only worth 5%, but it's the 5% that's worth getting because it's very easy. Homework, they just release a set of questions. It's usually like 4 or 5 questions. Usually you can answer most of them just by Googling it. Pretty much as long as you attempt it and show that you've done all of the questions, when you get to class, you'll get the marks for it. Another part of that homework, which is kind of unofficially, but you have to finish the exercises you do in class. So pretty much in order to be able to leave the tube with marks, you have to do any exercise they tell you to do during the class. Rock lab, just show up. It's an hour or half an hour or something. You look at rocks, you nod your head, and then you're like, cool, done. The quiz, it's drawing. It's all about drawing. It's where you need to use your coloured pencils. Please use your coloured pencils. I can't say that I did, but I'm pretty sure I got bonus marks because I used coloured pencils. My breakdown for the quiz was use small sketches. So for example, if you have your big U-shaped valley like this that you've drawn out, go in and draw a smaller view of what just down here would look like. So you could have like a stream down the middle or something like that, which this is the side of that U-shaped valley. Go in and draw perspective drawings as well. So like the more small drawings you have, the more likely you are to have explained every part of that geological setting.
This is for the quiz.
For the quiz, yeah. The next thing, you need to think about what rock type you were given, because it'll be based on like one of the numbers in your student ID, usually. How that rock was formed, so whether it's igneous intrusive, so it was formed cooling down slowly, marking those types of things down is really good. They really like that. Thinking about the types of defects that you would find in the rock and why you would find those defects in the rock. So for example, you might find granite where a convergent oceanic plate meets a continental plate, because there's a big area in here which can have magma that cools slowly. I don't know where I was going with that. Defects. I lost my train of thought on that. Anyway, think about what defects the type of rock would have. Can I change screen really quickly? Would that follow my change?
Yeah. Yeah, just change it. I'll zoom out on this.
Where is it? Yeah. Geology quiz.
That's it.
Okay,
I'll just see a picture.
so pretty much all of these are past papers of the quizzes. They should all be released to you with solutions and how Kurt marked it. I went through and started just looking at rocks. So like all types of rocks, you can pretty much get given anything. There's often from past quizzes you could kind of see trends in what rocks they were giving you, but in reality you can actually be handed any rock. So you actually just need to do a little bit of research on different types of rocks, how they're formed, typical defects that form in them, all that type of stuff.
Closed book, right?
Theirs is closed book, yeah. Yeah. But yeah, there's, for example, this one. He's highlighted all the important things in red that he would have pointed out in this quiz.
He's red.
Oh no, this red. Yeah. So he actually does really well in terms of prepping you for the quiz. It hasn't changed that I could see in the last about 5 years. So it's pretty, you can feel pretty confident going in that it's going to be the similar type of quiz. Where is it?
Can we zoom?
Oh, yeah, you zoom.
Yeah, I'll do it.
And then you also need to think about the boundary conditions between the rock and the soil that's there. So like, will it be very weathered? Will it not be very weathered? Will it be rough? Will it be smooth? Things like that. And then you also need to think about structures that you've been asked to put in. So usually you get asked to put in a dike or something like that. Sometimes it doesn't really make sense. For example, I got given a dike, but I also got given an alluvial floodplain setting. So like, usually those two don't go hand in hand, but you just have to go with it. So I kind of put my dike up the middle and then said the areas on the outside would have metamorphosized. And then there's like the grey area that I was talking about before, and then there's the bedding planes of the sandstone. So you kind of just like in the moment have to think what would happen with those features. And also do not forget to put your water table in. The water table line is very important. He gives out like 5 marks just for that water table line. So always think about where it is. If you have a valley like this and you have a river down the bottom, that's not a very good example. If you have your river coming down this way, I got given a river and floodplains on either side. These are my floodplains. I also got given a like flood event. So you have sort of like banks almost that happen there as that sediments build up here, bigger sediments, because they get dropped further in a flood. Where was I going with this? Oh, water table. The water table will stay at the river line. So it's not like the water table is going to come up into this little heap of soil up here. You got to think, how would that stay up there if there's no water here? Does that make sense? So like, almost the bank, right? River is here. Your water table line is staying with where you can see visible water. It's never going to be like, the river's here, my water table line is up here for this, because there's no water here. If that makes sense. Yeah. And then the Bronte field trip, make sure you take that printout, make sure you pick your group wisely. Same as a poster, it's the same group for your Bronte field trip and your poster. The poster, usually it's pick a geological setting that's quite interesting and then make a poster about it. It's like how it was formed, things like that. I think my group went slightly wrong in terms of, we picked the Leaning Tower of Pisa because we were like, that must be cool. Like the tower's gone all funky because of differential settlement. Turns out it was just all marine and alluvial sand that had just settled, and it was really uninteresting geology. So pick an area of like geological interest. Usually where two different orthologies meet is quite interesting. So like where you have a dike and sandstone, because they're like quite different. But yeah.
I think my group did Iceland, like this, like park in Iceland, like this national park with really interesting geology, or like online.
Was that the like hexagonal pillars?
It's like Fingleva or something.
No, I don't know.
And then yeah, it just has like basalt from like volcanic eruptions and stuff, and it's just yeah. And then we got given a note in the assignment, like good choice of place or whatever.
Yeah, we did.
And we got a good
We
one.
still did fine. I'm not saying we like bombed it or anything, but like I feel like we could have done better by picking a better place.
They don't like it when you pick like the Grand Canyon. It's like if it's the first thing that comes to your mind,
Yeah.
it's bad choice.
Brainstorm like 25 places and cross off the first 20.
You only have to do one, so
You only have to do one.
So probably
Yeah.
do like pick one.
Good things to know, the PowerPoints are different from the PDFs in terms of cursed notes. The PowerPoints are more set up to present like lectures, but they do have some interesting facts that aren't in the PDFs. The PDFs are like the bare bones of it. So if you want to read more, go in and read both. Ask Kurt questions. I found him really nice. He was really responsive. He's quite blunt in the way he says things, but he's really responsive, and he really appreciates people showing an interest in what he's teaching. Yeah, so he really leans into it when people ask questions. He also, I think he still is the industrial partners manager person. So like,
Right, Sue?
for example, when we had the careers fair last year, he was walking around there. He also often offers to edit resumes, cover letters, anything to help you get industrial placement. I don't know if you guys might be working already, but he's a really good person in terms of that. He completely edited both my resume and cover letter. And said he was also a reference for my job, even though I had it before. But yeah. That's it for geology.
Alright, round of applause. Thank you very much. Let me just stop recording this one. I'll try my best to speed through it, because some of it overlaps a little bit with what Millie was saying. But first, let me just check I'm recording. Yep. Okay, so the first thing to note is that you've probably heard about this printout before. In week 7, maybe on Monday, maybe this other week, maybe later in the week, they hand out these printouts, and you want to grab a copy of them because it's like a limited amount. They're nicely like printed in color with like binding and stuff. And but there's like online copies as well in the middle. But it's basically the Geotech Bible. So for the second half of the course, everything you need to know is in that book, and it's really well presented as well. Yeah.
Pretty much in my company, maybe 60% of the people who work there went to UNSW. Everyone still has this on their desk. On their desk to use.
No
It is.
It's really good.
Yeah.
And
Did Kurt make this?
No.
Baba, right?
I reckon it wasn't in the back. I reckon it was
It's probably a combination.
online or NASA or something.
The Musketeers,
Yeah.
the Avengers. Okay. So yeah, just keep this in mind. Really, really useful. I know Millie talked about this, but we're gonna quickly brush up again on it. I just want to tell you that research skills, when I say research skills, is because for part A of your assignment, that's looking at a place which you're not physically going to go to. Like for me, I'm not going to go to Iceland to like do my assignment, right? Yeah, and Millie's not going to go to, what was it? Italy, right? Yeah, exactly. So that's all about research and being able to find good resources on like Google Scholar or whatever. Practical skills is like doing your site visits and stuff, as well as the workshops in the first 5 weeks is all like hands-on, like practical, like inking in like 3D or whatever. Just like pretending, like role-playing that you're a geotech engineer. And yeah, in terms of technical stuff, that's for the midterms, so like what Millie was talking about. That's all drawings, right? this course is going to do a complete 180 and become soil mechanics part 2 in the second half. So that's applied geotech, which will just be the finals material, right? Here I've broken up the week's content. So the first 5 weeks is what Millie was talking about, right? So those words should seem relatively familiar, except maybe I stepped in a bit late, but that's how the course is laid out. Here, in the applied geotech part, we have the overview and review of soil mechanics, or like the overview of this part of the course and soil mechanics review. That starts out pretty chill. Actually, that could be week 5, did you say, right?
Yeah.
It's actually week 5, not bad. And then it starts talking about these words here. I'll highlight them. It starts talking about foundations, retaining walls, things like this. So these are earth structures. That's kind of the crux of this half of the course, essentially, right? If I'm scrolling too fast, in the chat on Messenger, there's a copy of my notes. So if I scroll past whatever you need, just refer to that. But earth structures, like, think about this, right? What would they be made out of? Like these things, shelf foundations, piles, retaining walls. Anyone?
Soil.
What do you say?
Soil.
So they're built on soil and they're built on like rock, but like more specifically, right? Because you've done concrete, right? So,
Concrete with steel?
yeah, it's reinforced concrete structures essentially, right? That's what all of these are made out of. And so this is a really interesting intersection between reinforced concrete and soil mechanics, essentially, and geotech and stuff. Here's an example of shallow foundations, which is the first topic we talk about, right? So from this list of types of footings, which I've listed here, what type is this photo? I'm just going to pick on people. Jess, what do you think this is? Yeah, that's right. So there's actually a few words for this, but it's an individual column footing. So this is also called a pad footing. It's also called a spread footing. So they're the same thing. That's this one, right? And I also want to touch upon this one because it's going to be in the course. I think combined footings are also in the course, but there's another word for this one, right? So that's a wall footing, but it's also called a strip footing, right? And essentially, the main difference between these things, I'm going to call these dimensions, like this is B, this is L, and this is D. So D stands for depth, like the depth of the concrete. That makes sense, right? Because it's like the vertical axis. B and L, right? So this kind of looks like a square, but pretend this is a rectangular pad footing, right? What do you think B and L refer to?
Breadth and length.
Yeah, breadth and length, or you can call it width and length or whatever, right? And there's actually kind of like a hierarchy here because B, the width, is always, at least in geotech engineering, and actually, like, fun fact, I did advanced concrete in terms of last year, and they, like, one of, like, the last 3 weeks of content is designing footings and retaining walls. So even in advanced concrete, you do geotech. So in that course and in this course, B is always smaller than L. B is the least dimension, right? D, the depth, is always the vertical direction, but B and L, from those, length is going to be the longer dimension. Yeah.
What is like the purpose of, like, what is it footing?
That's a really good question, actually. So, so this is called a foundation, right? So, we're talking about shallow foundations. Below, there's a bit of a spoiler there. You can see pile/deep foundations, right? Essentially, heavy structures are going to sink into the earth, right? And sometimes you might be building on suboptimal terrain, right? So you have these foundations in order for the building to not move, right? It spreads out the forces. So if you can imagine this is a column, the weight of the building is going to be transferred like this and then distributed so that there's like minimal settlement and stuff like that, right? Yeah. But yeah, like I think you only really need to look at these first 3. These are like the main ones. With a wall footing, we have depth like normal, like before. And can someone tell me what these dimensions would be? Maybe David. What do you think these dimensions would be?
Not the breadth and width, right?
Yeah. So this would be breadth. This would be width. So
Length, rather?
so breadth and width are the same thing.
Okay.
This would be length, right? So the longer dimension is the L.
Yeah.
But for a wall, essentially we're saying that we do our calculations per meter, so per meter of this length, because this L is like extremely long. Like it doesn't matter how long it is, it's a strip. So like, yeah. When you see a strip footing, which you'll see in the question, which I'm about to do, the L dimension effectively doesn't exist, or it does, but it's like so long that we just don't consider it. And we do the calculations per meter, like per meter going that way. You know what I mean? Like 96 kilonewtons per meter that we designed that way. Right. Yeah. Any questions about that? I'll quickly touch on these ones, but I'll get to the calcs first. So piles or deep foundations. When would you need this? Like, as opposed to a shallow foundation. Shara, do you want to crack at this?
If you're building underground?
Maybe. But like say you're building like a big building, right? And for example, this is all weak soil, this is weak soil here. And this is like strong soil rock. You kind of want to embed your building into the strong foundation so it doesn't move, right? Especially if it's like a really big, heavy building, like a skyscraper or something, right? That's when you need a deep or pile foundation. And here I've just included, I don't know, in my 2101 assignment, so this is back in, second year construction, one of the construction equipment which I analyzed was piling rig. And yeah, that's where they have like the big drill thing, and it drills into the earth. You insert this like steel cage into it, and then you cast concrete. Very similar to like any other reinforced concrete structure, but usually they're cylindrical. That's what a pile is pretty much, right? But it's for the sake of being a foundation for a building or whatever. Okay, all good? Okay, we're gonna fly through this, guys. One more thing is, that's a pile cap. So these were the piles I talked about here. And like this concrete structure which you cast, right? It's reinforced, and it's just to like combine the piles so that they like are one structural element, and then you have a building which is structured, right? Yeah.
So what is
So this might be like a rectangular concrete wall, and it's just to stitch together these concrete elements into one structure.
like is this a deep foundation?
Yeah. So these piles are the deep foundations, and then this is the pile cap it off, right? What's we got here? Retaining walls. Okay. So the important thing is that there's two words you hear a lot, is the toe and the heel, right? We talked about fill with Millie's part. So fill, like backfill, is maybe when, have you seen those retaining walls like where you're driving through like the highway in like rural New South Wales, and you have to cut through like a mountain or whatever, and they have to build retaining walls so that the earth doesn't collapse in on itself, right? So the backfill is, I guess, the higher end, or like where they've put in a bit of earthwork to like fill it up, and then and then so the heel is the side of this retaining wall, which is close to the backfill, and then the toe is like that. There's a few types of retaining wall designs. I'm pretty sure this is a cantilever, right? Sometimes it's called a toe and heel, right? Toe and heel retaining wall, but that's probably what you'll deal with in the retaining wall portion towards the end of the course. Shara, do you have bookends in your home library?
Yeah.
This is basically a cantilever retaining wall. right? If you think about it, because, you know, well, like, just think about what the books are doing, right? You want to, you know,
Like keep them together.
yeah, like, because you don't want your books to, like, fall over, so you put the bookends in. The book's weight is stopping them from going, like, sideways from this bookend design. That's what it, yeah, you're doing the same thing with the soil, pretty much.
So which end is which end?
So it's kind of like this more so. It's a cantilever wall, but there's no toe. There's no toe basically in this bookend. This is the heel side, which is towards the back. Because the gravity, like the weight of the back heel here, is going to squash down and stop this from wanting to overturn.
So it's because you're squishing down on the floor underneath the backboard.
Yeah. Oh no. Sorry. This is one concrete structure, right?
Oh,
And the weight of the soil is going to keep this part from wanting to rotate like that, right? Yeah. It's called an overturning moment. Actually, you see it in the next bit right here. These are the ways that a cantilever, like a toe and heel retaining wall can fail, right? What I'll do, since I'm limited on time, is I will quickly write this down. Yeah, like I'll be honest, like this is kind of pseudo because like I didn't have like this much time to like cook up the course. But this is kind of a combination of what I remember from advanced concrete. When you're designing not a retaining wall. I learned this. Okay, this is sorry. Don't quote me on this. Basically, with these earth structures, the two main ways it can fail is actually now that I look at it, the only way it's described here that it can fail is due to the soil, right? Like these are all like excess force from the lateral earth pressure of the soil here. Here it's overturning and burning at this point. And then you have like, actually, you know what? I'm just gonna stop talking. I don't know enough about this topic, sorry. Yeah, in advanced concrete, what we learned is that the concrete itself can fail. The concrete itself can break. And so you have to check both like the concrete strength as well as the soil and like the methods the soil can fail in. But I think in this course it's just the ways that the soil can fail in. Yeah, so sorry, don't quote me on that one. Yeah. Okay. Oh, sorry, did you need to copy that now? Okay, so geotechnical design criterion. So we've finally gotten into where the book picks up, right? This is like the first part of the notes, essentially. And Sue, because I know that we did concrete together, right? What were the kind of design criteria for concrete back when we did it? There's two main ones. The words are here.
Serviceability.
That's one one.
Strength.
That's right.
Oh, really?
Yeah. So, one, the strength criteria is based on, at a certain point, it's not strong enough to withstand, like a large load or whatever. So this is like, yeah. But anyway, so the serviceability criteria is to do with like everyday loading. So like slow deformations and stuff over time. And it's kind of governed by soil settlement and, I mean, if you kind of remember this graph, you have your stress strain. This is essentially stress strain, but a bit modified. The settlement is basically to do with your sort of strain. What do they call this? Delta E, right? Yeah, stress. Instead of stress, we're talking about forces or moments. In the case of the overturning moment. And then here we're talking about it in terms of deformation, how much it moves, pretty much. And so these are the two limits that we're designing for. And yeah, like to put it into a kind of like example, SevStock budgeting, right? So there's some events in SevStock that you run that you're just trying to minimize losses, right? It's gonna be a loss no matter what. And there's some that you're trying to turn a profit. That's kind of like this, like you're given a job and you're trying to either design for the strength or the serviceability. So like how much it's gonna move, right? So it's like, oh, we want this to not completely get fucked, or like we want this to be under some sort of like settlement limit. So these are just like different things you're designing for pretty much. Same thing with like this budgeting analogy that I'm trying to go for, right? Yeah. Yeah. And with how the course was broken up, if I go up here, with how the course was broken up, you'll see that you have bearing capacity of shallow foundations and settlement. So bearing capacity is, which one, David? Of the two things I talked about. Oh, sorry. So like between bearing capacity of shallow foundations and settlement of shallow foundations, which one might be like the strength design criteria? Which one might be like the settlement design criteria? Sorry.
No, it's a bit confusing.
Oh, sorry. So bearing capacity is like how strong it is, pretty much, right? So the strength of the shallow foundations, right? Whereas the settlement is the serviceability criteria for design for, because it's about how much it moves, like the earth moves. So that's kind of how the course is working on that. Pile foundations, we'll talk about both in that one topic. Yeah, I think the majority of it is bearing capacity. Bearing capacity is just another way of saying the strength of.
Like strength design, right?
Yeah, the strength
Of
design.
the foundation.
Yes. Yes. I had to think about that for a sec. Yeah.
But you're imagining not the foundation fails, it's the soil around it fails.
Yeah, that's true actually. Yeah, that's true.
In geotech, it's not our problem if the structure itself fails, it's our problem if its amendment fails.
Yeah, so again, advanced concrete structural course, that's calculating your reinforced concrete breaking. You just assume that doesn't happen here. Yeah. Okay, yeah, I'm just gonna, there's like factor of safety stuff, which you learned a little bit about in soils. I'll just draw it out here. These formulas make more sense when you do the questions. There's basically a few methods. So this one's the factor of safety method. This one is, if you guys have done like steels and stuff, this is like what they use in steels, although you usually don't see it in like this like super theoretical way. This is like a few different ways that they tell you, that they outline on how to calculate capacity versus loading. So to recall an example that Will gave for the steels course, crash course, if you were to design, for example, scaffolding, right, for a construction site, and you wanted to design for 300 kilograms, say that's like 3 really heavy lads that all weigh like 100 kilos. Would you design it so that it can resist exactly 300 kilos? No, right? Because you want to design it so that they can like withstand a bit more, so that there's like a bit of safety involved, right? So that's like the whole idea with structures. You have, just to talk about structures, this is what they use in structures. That component there is your reduction factor, and that reduces your capacity so that it looks a little bit, you underestimate it a little bit, you know? So maybe like, anyway. And then this one, this is to exaggerate your loading. So like, instead of like three 100 kilo lads, we pretend that they're like 3 150 kilo lads, but my section and whatever for the scaffolding should be able to withstand way more than that, you know, like you have these like things in place. But the good news is for factor of safety, there's only one part of that in this equation, and they just give you one number. So it'll be like designed to a factor of safety of 2, designed to a factor of safety of 3, whatever. So you just like, that's the number that you reduce your soil strength by, like the soil strength around your structure, right? Yeah. And I think Millie said earlier to me that this is something that they just give you in the questions because, I said that, and then she said in real life, your client will just give you like, oh, we want to design to a factor of safety of 2, we want to design to a factor of safety of 3. So it's just what the question tells you because that's how it works in real life pretty much, right? Yeah, I'm not going to talk about this shit. Okay. This is the most fucked looking formula of all time. But we'll break it down because it's actually not that bad. Because most of the time, and especially in the general case, this is not like, you don't have to calculate most of these things, right? And they're from this table, which I'll show you below. Oh my god, sorry. So if you notice some patterns here, right, I'm gonna just go through the colors. So basically, do you see how it's just the same thing but with different subscripts. So you have 3 components here. This C denotes soil cohesion, okay? And then this Q is to do with the surcharge component. So the surcharge component, soil cohesion component. And this one is to do with the unit weight of the soil. Okay? And this B, like we talked about, is the least dimension of your foundation. So this whole thing, with calculating the bearing capacity of our shallow foundation, this is for your like pad footing design, your strip footing design, these kind of things. And you'll notice as well that each of these components has an N. N just stands for like a factor that you find from either an equation or the table. Okay. So I'll explain these later, but N has these equations, right? But the good news is you don't have to calculate these unless they give you a weird angle. Because this table gives you the common values. So these are all like, your potential angles that you have to calculate. And you just go across and find what all these numbers would be. It's not bad, right? This part of the table here is used to specifically calculate one of the factors, dq, which you'll see below. But yeah, let's quickly talk about what all of these things mean. Your shape factor takes into account the shape of the footing. So whether it's a circle, a rectangle, or whatever, there's just like a number associated with it, right? Which will increase or decrease the strength of your, your strength pretty much, right, in this design. The depth is to do with how deep, so we're looking at an elevation view, right? How deep your foundation is into the earth. It'll increase in strength because it can, it's being squashed by the soil and stuff, right? So it can, it's like, takes on more strength pretty much, right? Your inclination, ground, and base factor, you can have a read of this later, but it's to do with the angle of how the ground's angled. But for the example, you'll see that everything's flat, so you don't have to worry about these factors at all if the ground's like completely flat. And inclination factor I'll quickly talk about. That's if your forces are being applied at an angle, essentially. But if it's being applied like bang on, right? All of these will just equal 1. So it's fine. Does anyone have questions? Because this is a very important equation. This is like your Bernoulli equation from back in fluids. Like you use it all the time, right? Cool. Oh, and one more thing. For saturated conditions, right, so undrained conditions, you use this like there's a simplification for this whole formula, and you'll see that it says like CU. CU is from this part of the table, right? Whereas the rest of the factors are from the bottom parts of the table. It's just like looking up shit. You like go back and forth, you do enough practice and you'll get it. So yeah, obviously we're running over time, so we're not gonna have time to do the actual question, but yeah, and you can look at this later. This is just an alternative. That's called the Tiragazi method or whatever. Oh my days, it was so hard to get this this photo. I like took a screenshot of the video because I couldn't find the. Anyway, this is like really blurry basically, but it's a strip footing, and therefore your length is way bigger than your breadth, right? Or your width, and it's way bigger than your depth as well, right? This is just strip footing. And they want you to find QU, which is what we're calculating. This is the soil bearing capacity. And it tells you like factor of safety 3. So in the question, yeah, they'll tell you like factor of safety 3. The question itself doesn't look that bad, right? And you'll note that even like if you look through the booklet that you're given, it looks like there's just like so much shit. Like it's overwhelming, like the amount of detail that they go into. When you do the question, it's only like 3 sentences long. Like it's not that bad, right? And my working is maybe like 2 pages long, which isn't bad compared to like Jesse Room like steals or whatever. It's fucking pages and pages of working on it. So it's not that bad. Like each individual question doesn't take. It's not that bad. And you have to note that when you're designing a foundation, they give you this elevation like side-on view, and you have to do your calculations for surcharge based on the left and right-hand side. So there's like different conditions here. Here you have this like external surcharge load. It could be from a building or whatever. And here, there's like additional like earth levels with the it's a water table and stuff. Yeah. Yeah, and then you do your drained and undrained analysis. So use the different formulas. So for your undrained analysis, your drained analysis, you use the Hansen general equation. Your undrained, use the simplified version, which I forgot. And just plug in. You just find like looking up numbers on like where everything is, and then you just plug it in. Here I've cancelled out like fucking over half of these like terms. You don't have to calculate these, right? So you find out what you do have to calculate. Yeah, which in this case is like D, right? I think you always pretty much have to calculate D. So that's the depth factor. But yeah, the rest just turn out to be 1. And this is what Hansen's equation looks like after you scratch out everything. You look at the table, you refer to 25 angle, which should be like, it's here, sorry. So that's 25. And then all of a sudden you have NC, NQ, and gamma already. That's not bad. And you note down this factor, because that factor will plug into this equation here. For our example, our width is way bigger than our depth. So you use this top. So there's like a if this, use this, and then if this, use this. Alright. That's it. That's the whole question. And then like, yeah, there's like a few more nuances, but surcharges from soil mechanics, you calculate the minimum on both sides using your effective, weight and stuff. And yeah, that's it. And here at the very end, we do the factor of safety thing. So your allowable earth pressure is equal to what you calculated divided by factor of safety. That's it. Any questions? All right, we've made it. End of the crash courses.